Okay, in this assignment, we're going to be looking at how we show the net force on an object. The net force is kind of like the total force. Really, in physics, we a lot of times see multiple forces acting on an object at once. But we only see the object move in one way. So the way that the object ends up moving or changing its motion is kind of a direct result of all the forces acting on that object at the same time. So we use force diagrams to show all the different forces that are acting on an object, in what direction and in what magnitudes, like what strength, so that we can figure out how an object is going to move or change its motion. Okay, so as a reminder of some types of forces that we have, and we might see on these diagrams, we have the force of gravity, which pulls objects down towards Earth's surface, and technically even towards the center of the Earth, but to us, we stop at the surface. Normal force, which is when a surface pushes back on an object. Most of the time in this class, we're going to see that coming from objects that are resting on a surface, like a table, on the floor, on the ground. So it's going to be that surface pushing back as gravity pulls them down against it. We have applied forces where something separate is pushing or pulling on the object we care about. So, if we're looking at how a box is moving, then something other than the box is pushing or pulling on it, and so that force is applied by something else. So that's an applied force. Friction force is something that opposes motion on a surface. So when an object is, say, sliding on the ground or on a table or something like that, whatever direction it's moving, there's going to be an opposite force pushing the opposite direction of which way it's moving, which is going to accelerate it in the opposite direction. In other words, it's going to slow it down. Okay, air resistance is kind of the same idea, but instead of being on a surface, we're dealing with something that is in the air. So you can think of air resistance as kind of like friction, but in the air. When something is moving one direction in the air, you have air particles that are bumping into it and making a force that pushes the opposite direction of that motion. Tension force is a force that comes through a rope, cable, string, a chain, something along those lines, that is pulling on an object. So like if a box is hanging by a string, then the string is pulling upwards against gravity, stuff like that. Let's go down a little bit more. Okay, then we also have a spring force, where a spring is doing the pushing or pulling on an object. It's a lot like the tension force, but with a spring. It's like a slinky, basically, that can be compressed or elongated and uncompressed, stretched out, and that can cause forces. Okay, if you are drawing force diagrams, these are some things that might help you out. There should be a little sentence or two that should tell you kind of what's going on with the object, whether it's already moving or not, whether it's on a surface or it's in the air, if it's in space. And so that should allow you to see if there's any forces you should ignore. So maybe there's a hockey puck sliding on ice. Well, that ice might have such low friction that we just basically ignore it. So the problem might say, hey, draw all the forces, except don't worry about friction because it's not really affecting things. Okay? Or you might have something floating out in space, and it might say ignore gravity because out in space we're not close enough to any giant body like a planet that would cause a significant gravitational pull, so we just don't draw the force for that. Or maybe something is traveling through the air and it's very aerodynamic. It's very sharp shaped, so it flies very smoothly through the air, and so we might ignore air resistance. So just pay attention to the problem and see if there's anything you should ignore or write out. If you already have a force diagram, then you don't have to worry about that as much, but it does still help to read the problem along from just looking at the diagram to get all the information about what's happening and what the object is. Helps you kind of imagine the situation. Okay. Unless you are in space, gravity is always going to be pulling down. So if you are making a force diagram or choosing a force diagram that fits the situation, if gravity is not a part of it, it probably should be, unless you're in space. So it's a good way to kind of check stuff, make sure gravity's pulling down on objects on Earth. Surfaces push back on objects. Okay, so if you have gravity, say, pulling an object downwards, then you're going to have the normal force pushing back upwards. Unless there's nothing underneath the object, like if there's something falling through the air or flying through the air, then there's going to be no normal force in that situation because there's no surface to push back against it. Okay, but if something's just sitting on a surface, whether it's moving or not, you have normal force pushing the object back, which is why it doesn't just sink into the table or the ground or something like that. Okay, if you have a moving object that's on a surface, it's going to be slowed down by friction. And if you have a moving object that's in the air, it's going to be slowed down by air resistance. Again, unless the problem tells you, like, hey, not in this case. Okay, so let's take a look at this assignment. Got 3 attempts, that's good. Alright, so there's the notes again. Alright, let's look at this first set of problems. Okay, so in a force diagram like this guy right here, these arrows that are going kind of up and down here are used to show the amount of force on an object. That's why they're called force diagrams. Sometimes they're also called free body diagrams, and that doesn't kind of tell you the force thing is right out. But usually also we'll have kind of next to the arrow an F for force and then a little subscript there to tell us what kind of force it is, like gravitational force or the normal force. Okay, so these arrows are used to show the amount of force on an object and in what direction those forces go. To help kind of show when things are already in motion, I use these little yellow triangles like speed lines in a cartoon to show that something is already moving or it's already in motion. Okay, so if you have an object that doesn't have those little yellow triangles coming out like this guy up here, that means it's just standing still in that moment when we draw the force diagram. Okay, so this box is in motion, it's moving towards the right, and so the speed lines are kind of saying like, oh, it's going this way. We also use a gray line underneath, or at least I do, to show that an object is on a surface, okay, that's sitting on something. Okay, whereas something that is just kind of hanging out with a line underneath it, like this guy right here, means it's out in the air or out in space. It's not directly sitting on something. Okay, so I use that gray line to show that something's on a surface. Okay, now the size of the arrow also matters. The larger the arrow, the stronger the force. Okay, so if you have a really, really big arrow, there's a lot of force being applied in that direction. And if it's a very, very tiny arrow, then there's not a lot of force. It's a very weak force. Arrows in opposite directions cancel each other. They act against each other. So if you imagine like you and your friend on opposite sides of a big crate pushing on it, you're fighting against each other. So in this case up here, if I have normal force and the force of gravity acting in opposite directions, they're going to cancel each other out. So if one direction of the force is stronger, or in other words, it has a longer arrow, that means the forces are unbalanced. That means that one of the forces is stronger than the other, and one of those forces is going to kind of win out and cause some new change in motion where the object's going to accelerate in some direction. There's a net force that's winning out in one direction or the other. So the object's going to accelerate, which means speed up or slow down, in that direction, whichever has the stronger force. You can kind of imagine it like a tug of war here. So here we've got a box that's got a force applied to the left and to the right, so those are acting against each other, but the force applied to the right is stronger. So really we're going to have motion where the box is going to accelerate towards the right. Even though there's a force also applied to the left, it's not strong enough to beat that force applied to the right. So the net force, the way we're going to see this move, is it's going to start moving and it's going to accelerate to the right. Okay, you can tell it's not on a surface. It's not already moving. There's no little speed lines coming out of it, no yellow triangles. So it starts still, and then it starts moving towards the right, towards that stronger force. Okay, if forces on opposite sides are the same strength, in other words, the same length, the object won't accelerate, okay, because we call those balanced forces. The forces are balanced instead of unbalanced. Instead, it's going to continue staying still, or it's going to continue moving at a constant speed. Okay, so this box down here, our force of friction and our force applied are the same length. Okay, in other words, that means the same strength. So whatever force we're applying towards the right is going to be matched by the friction force going to the left. So going left to right, we're not going to be able to speed up or slow down this box. We're not applying enough force to get it to go faster. The friction is not strong enough to fight against it to slow the box down. Instead, it's just moving at a constant speed. Same goes for the normal force and for the force of gravity. They are balanced. They're the same length, the same strength. So we're not going to see any motion upwards or downwards. It's just going to stay still going upwards or downwards. It's just going to stay kind of in the same spot up or down from that surface. It's just going to stay on the surface. Okay, so if something is not moving in a direction and the forces are balanced, then it will continue not moving. Okay, like how our box is not going to magically just jump up off of the surface or sink through the ground. But if it's already in motion and your forces are balanced, that just means that it's going to continue moving at that speed. So it's not going to speed up, it's not going to slow down, it's just going to keep going at that speed, at that constant speed. Okay, so that's kind of the layout of force diagrams. Even though we always show this as a square with a dot in the middle, this can be used to show a lot of different objects. It can be something as simple as a box, but as complicated as a person. This is just kind of an easy way to simplify the object, so we're not too worried about how it's shaped and how that affects its motion, stuff like that. It kind of simplifies things. We just take all that mass and shrink it into the size of a box and say, okay, if we just imagine that this object is a box and then we move that around, it's a little bit easier to see all the forces acting on it. Okay. On this next page, we're going to be matching up some forces. So let's see, we've got a box with an applied force to the right that's kind of weak. We've got a box with two applied forces, one to the left, one to the right, and the left force is much stronger. And we've got one in the same situation where the stronger force is to the right. We've got one where the forces are equal, and then one where we've got a force to the right, and the box is already moving towards the right. So let's see if we can match some of these up. Two forces are applied in opposite directions. Okay, so that could apply to a couple of these. So we have forces applied in opposite directions here, and here, and here. So it could be any one of these three so far. Let's see. Since the two forces are balanced, okay, so we want the forces to be the same strength. Okay, the arrows should be the same length. The object will not move. So let's check this here. Okay, well, this is, I think, the only one where the forces are the same length, the same strength. So it must be this one. We're talking about this force diagram with this description. Okay, the box isn't moving yet, and since the forces are balanced, it's not going to start moving. So the object's not going to move. That fits pretty well. Let's try another one. Two unbalanced forces are applied in opposite directions. Okay, so it can't be this bottom option because we just have one force there. If I remember right, this top option, yes, only has one force applied too, so it can't be either of those. It's going to be either this one or this one. The force to the right is stronger, so the object's going to start moving and accelerate to the right. Okay, so it's going to be this one right here, where we have a stronger force to the right. The box isn't moving yet, but it is going to start moving in the direction of that stronger force. It's going to go to the right. Let's see, a small unbalanced force, okay, just one force, is applied to the right. So the object will start moving and accelerate to the right. Okay, well, this box is already in motion. It's already moving. So whether you call this a weak or a strong force that's unbalanced, it's not going to match this description because we want an object that's going to start moving, not one that continues to move. So what this is going to match is this option up here. Okay, where we have the object that's not moving yet, but it is going to start moving towards the right, and it's going to accelerate. It's going to speed up as it goes to the right. All right, a large unbalanced force is applied to the right. Okay, so not two forces. So this is going to describe this guy where the object is already in motion. It's going to continue moving, and it's going to go faster as it moves to the right, which means we have one option left. Excuse me, sneeze there. So we have two unbalanced forces, except this time the one to the left is stronger, so it'll accelerate towards the left. Okay. The more you do force diagram examples like these, the easier they get. So practice is super important with these. Okay, you'll start to recognize patterns and things. Even though there are quite a few different kinds of force that we can throw in here, force is force in the end. Whether you call it applied force or tension force, the way that it causes things to move just depends on the strength of the force, not the type. Okay. The type of the force might help us predict where the arrow is going to go, like we can expect gravity to be pulling downwards or something like that. We can expect friction to be going the opposite direction of whatever way the object is moving or trying to move. But other than that, force is force. So you'll start to notice kind of a pattern of, you kind of see force diagrams that either go one way or another. So the more you do, the easier they get. Okay, the last couple questions are just trying to pick a description that best fits the diagram. So let's see here. We've got a box here with gravity pulling down, tension going up. It starts by not moving. And so based on this tension and gravity, well, since the force of gravity and the force of tension are balanced, they're not going to have one side winning out over the other, so the box is not going to start falling, and pulling away from the rope. The rope is not going to be pulling so strong that it pulls the box up. So our box is going to hang, and it's still not going to move. Let's check another one. Let's do... Well, that's a little bit different. Let's look at this one. We got a heavy stack of books sliding to the right across a table. Okay, so if this is our stack of books, we've got gravity pulling down, normal force going up. So kind of like the gravity and tension example, those are balanced. So the stack of books isn't going to be moving up or down off of this surface here. It is already moving to the right, okay, but we also have friction acting towards the left, okay, against the direction of the motion. So we don't have an applied force here. It's already in motion. It's already sliding. But then we have friction going against that motion to the left. So our books are already in motion, and they're going to be slowed down by that opposing force. So let's see. Stack of books will keep moving right, but will be slowed down by the unbalanced friction in the opposite direction. That sounds pretty good. Let's just check the other examples to see, other answers to see if they sound good. Since friction is acting in the same direction as the motion, no, that would be weird. If you had something rubbing up against the surface and it caused it to go faster in the direction it was already moving, that would be kind of odd. Stack of books will change direction. Well, maybe if you had an applied force on the other side, but no, friction only opposes the motion. So if it slows down the box enough to stop, it's not going to start suddenly moving to the left. It's just going to stop moving. Okay. Since there are balanced forces up and down, some of the books will move upwards and others press harder on the table. No, we're going to treat this all as one object. So those balanced forces just mean that we're not going to see a change in motion up or down. Okay. And there's just two problems left. So again, look for how these arrows compare to each other. See which side is winning out, or which two sides are winning out, which may cause it to kind of move diagonally, or whether things are balanced. I've tried to kind of make the arrows the same color if they're the same size, so that way you're not trying to like measure out on your screen with a ruler, like, oh, is this exactly the same length as this arrow? They should be if they're the same color. Okay, so like on this problem, if they're different colors, I'm trying to show you that they are different lengths. Okay. Now, something to keep in mind with the options I showed you, with the multiple choice, these might be shuffled on yours. They might be in different orders. So if you're following along with the video, please don't just be like, it's the first one, and then click on that, and then go to another form, like, it's the first one, and click on that, and then it might end up being wrong. Make sure you actually read your options before you pick them. Okay. Other than that, your forces will tell you what's going on with the object. So read your forces, read the strengths, see what's winning, what's losing, what's balanced or unbalanced, and then make sure you check and see if it's on a surface, if it's already moving, and then figure it out from there.